So just a reminder, the quiz is now officially, again, an individual pursuit as usual. So it is a take home. So you'll put it away now and you'll take it home and you'll work on it at home. The only thing you can use at home is your calculator and an index card if you've already made an index card, but don't just go and make an index card now that you know what the questions are on the quiz. So the quiz will be due first thing on Friday morning. Take as much time as you need, but you may no longer communicate with anybody else in this room or in any other room. So a couple of announcements before we jump in. First, a reminder that there is this problem-solving forum happening at noon today called Salvaging the Semester. So if this class or any other class or all of your classes are not going as well as you would have hoped, this is an opportunity to try to problem solve and figure out how to turn things around. Again, it's happening at noon today in C208. Free food. Any questions on this? Okay, yesterday was advising day, just for my benefit. Can I get a show of hands if you came in yesterday for advising day? Just to come in. Did anybody come in? All right, just a few. Tutoring is good. All right. Okay, so that is that. Next thing, there is a scholarship, $600. Actually, there are two of them offered by the GCC faculty and professional staff unit. I just want to highlight a couple of things here. You need to have a minimum GPA of 2.5. You need to have at least 12 credit hours behind you. You need to be currently enrolled, which you are. And then the last one here is what makes it special to this group. You need to have contributed to the improvement of workers' rights, equity, and justice. And I'm sure there's an essay involved where you explain how you have done that. So if you feel like you meet the criteria here, let me know and I can email you this document. Any questions on that? Deadline here is April 26th. So let me know if you want more information. There's a whole page worth of description about what you're supposed to do. Okay, that is that. Next thing is the calendar. So today we had quiz number 5. You're going to continue to work on it. Today we will finish up talking about probability. Next class, a couple of things are happening. First of all, project number 6 is due. How are we doing on project 6? I ask because this is the first time I have given this particular project. So I want to make sure it's not too long, not too hard, but it is challenging. Have we made progress? Have we looked at it? Is it? Okay, first two. Okay. Okay. So kind of confusing in what way? Can we get more specific? Okay. Mm-hmm. Right, all the little pieces. Right. Yeah. Yeah, I mean, so I definitely, if any of the directions are confusing, it's completely on me. I mean, I got the 3 problems from the textbook, but I added I broke it down myself into all these little pieces, and so I picked that language, and I tried to pick it very carefully, but if it's confusing, it's on me. So I'd like to know if there are questions about the wording. That's perfectly legitimate. Bring it to me and let me know what we are unclear on, because I really want to make sure that everybody's clear on the directions. Okay, so next class is also our review for test number 2. It will go as usual, where we'll just talk very generally for like the first 5 minutes of class about the test. Probably I'll also mention this handout that I gave you maybe a week ago or so. It was a supplement to class number 14. I handed it out and we haven't mentioned it. So we're probably going to spend maybe 5 or 10 minutes looking at this next class. If anybody doesn't have one, I can give it. And then we'll spend the bulk of the period just working in your groups with looking at the practice problems that are in the packet. And again, there are YouTube videos for those practice problems. And then the test is on Monday. Any questions on the calendar? And the test is on everything since test number 1 to include 2 snow days. So I hope you did some work on the snow. So it's all that stuff from test number 1 down to here. The project is due on Friday. Project is due Friday, 2 days from now. If you turn it in Monday, it's a 5-point penalty. It's not that big a deal. So if you want the weekend, it doesn't cost very much. Any other questions on the calendar? Okay, so then let's come back to where we were last class. We're here on page 53. And the last example that we looked at had to do with catching fish. So we go out and we catch fish every day, and some days we get 2 tons of fish, and some days we get 8 tons of fish. The most common number of fish we get is 6 tons of fish, and then there's those probabilities associated with all the different number of tons of fish that we might catch. And this thing right here was a PDF, a probability density function. And what that means is that if you wanted to find, for example, the percentage of days when you are between 2 numbers, like 7 and 8 tons, what does that mean in the picture? Is the area. That's what this picture is. A PDF probability density function means if you want to find a percentage between 2 numbers, you are finding the area between those 2 numbers. And that's how the calculus comes in, because we know area is a calculus thing. So all we had to do was find the area of that green trapezoid, and that's exactly what we did. Turned out the area was 0.15. 15% of the days we catch between 7 and 8 tons of fish. Okay, so related to PDFs are CDFs. So the function P of t is a cumulative distribution function, a CDF of a probability density function, P. It's really confusing now. We got capital P is the new thing we're about to define. Little p is the graph up there with the fish. So here's what it is. Capital P is the integral from -infinity up to t of p of x dx. So you integrate the function, find the area of the function from where to where? Where do we start calculating area? -infinity. So you start at the far left and you pick up area as you go until you get to some arbitrary variable t. So for example, how much area is under the curve? Now we're assuming that this curve right here, I'm going to draw in black the rest of this curve, which is down here, and it's all of this. We're assuming that on 0 of the days we catch less than 2 tons, and on 0 of the days we catch more than 8. All right, so the function does go forever. I've put the only important parts in this picture. So if you start picking up area as you sweep here to the right, how much area have you picked up out here? How much area is there between the curve and the x-axis? There's none. So we have no area until we get to 2 tons, and then we start to pick up area. So we haven't calculated this, but can you calculate the area in here? And in fact, why don't we start splitting up the group, because there's going to be a few calculations like this. So I would like some table to calculate the red area, some table to do purple, and some green. Just do that. Just every table do one of those 3. Okay, so we've got these 3 areas, and we're going to sweep and we're going to start to pick up these areas because we're going from -infinity to some variable, which is t. Just a variable, it's like the x. So as we start sweeping and we pick up all of the red, how much have we picked up? We pick up 0.1. By the end of the red, we pick up 0.1. So I don't know what color I'm going to use on something that's really got some punch here. Oh, maybe these guys are thick. Let's try that. Good. So as we pick up, we decided we were getting no area until we get to there, and then we start to get some area, and by the end of sweeping through the red, we have picked up 0.1. So 0.1 on this graph is right up here, and the end of the red is at 3, yes? So I'm going to go 3, and I'm going to go up to 0.1, and that's going to give me this point right here. And we pick up some area in between this dot down here and that dot up there. I'm going to connect it with a straight line. I don't know if it's straight or curvy. I'm just going to connect the dots. Then we get all of the purple. And how much does purple add? It adds 0.14. But it adds 0.14 to the area you already got. This is a cumulative function, just like we did on the first couple of classes of the semester, where you pick up and you add all the total. So how much do we get at the end of the purple total? It's 0.24. So at the end of the purple, I'm up at 0.24. End of the purple is at 4. So I'm going to go to 4, and I'm going to come up here to 0.24, and it is there. Okay, so here's a question I don't know the answer to. Is that a straight line? Is it the same slope or no? Looks like it's a no. Right, looks like the second one has more vertical than the first one does. So apparently it's not straight. So actually that probably means that the two straight line segments I've drawn weren't right either. They were probably a little bit curvy. And that actually makes sense because if you think about adding area here, just add like one little slice of the red. How does the area of that compare to the next little slice, whoops, compared to the next little slice of the red? What happens to the area of the next slice? It's a little bit bigger. So we're not just adding the same thing every time, which would be a linear blue curve. It's actually adding more and more. So really those things aren't straight, they're actually curvy. And as you go up and up and up, you're going to curve up faster and faster. I don't have enough room on this graph to put more, but what would the next number be? It would be 0.4, is that right? Because we're at 0.24 and the green contributes another point. Am I right? No, I'm not right. 0.42. So it would be up there at 0.42 and we'd keep going up and up and up. So I'm going to draw my blue curve again, but I'm going to not worry so much about the scale. Let's put these guys here. So we have 2, 4, 6, and 8. Okay, so let's plot a few points on this guy for the blue. Yeah, it's very much the antiderivative because we're doing an integral here, right? So it is an antiderivative, plugging in some variable up here at the top to represent capturing all the area until a point. So, okay, so I don't want to spend all the time drawing this graph. So we're just going to draw just a very rough graph here. So we decided we get nothing until we get to 2. Then we start to get stuff, and I think we've decided it's going to curve up and up and up. How long is it going to take? Like what number down here for the tons of fish before it stops curving up? Because we've decided it's going to curve and then grow quicker and quicker, right? Because we're gaining more area every time. Until we get to where? Where does it stop growing as quickly? It's up there at 6, right? If you take the last rectangle right before 6, that's the biggest rectangle you'll find. Then you take the next rectangle just after 6. It's still pretty big, but it's not as big. So you do still gain something. You're still going to increase, just not as fast. So we're going to increase until we get to 6, faster and faster. And then what happens at 6? It becomes concave down. Still growing because we still have positive area, but not gaining as much. And then at some point, as soon as we get over here to this piece, how much more do we gain? Nothing, because then we're back to the axis. And when we start gaining nothing, what happens to the total, this cumulative area? It's going to be flat. Right? We're going to get to some spot where we pick up the last thing, and then we're going to stay flat. And what is the magic number? You have captured everybody. Right now we're up to 0.42. It's 1, because we know the total area underneath any one of these PDFs is 1. So it looks something like that. Any questions on the curve? This guy looks like the logistic function. Logistic functions have asymptotes that they don't actually reach. This is not a logistic function because it definitely gets to 1 exactly at 8 tons. So the name of the function depends on the curve that you're given. Okay, so that is a cumulative distribution function, CDF. All right, so we're going to jump down to number 10, some observations. P prime of t, this is capital P, which is the function we just introduced. So if I take a derivative of this guy right here, you guys remember that we did stuff like that? Taking a derivative of something that looks exactly like that. What do we have? Little p of x is very close. Little p of t. I'll write it with the letters that we used to use. We did stuff like this. Derivative with respect to x of some number up to x of some function of t dt. I think those are the letters that we used. You guys remember that? And we decided that finding the derivative of this antiderivative, as Cole points out, basically they cancel. And so all you get, you start with little f, you go someplace when you find an antiderivative, but then you come right back when you find a derivative. And so we decided that this was actually just f of x, the letter of the variable, the true variable up at the top, ends up just going inside for t. Here the x and the t are swapped, but it's the same thing. So p prime of t is exactly p of t. Yes, your confusion is understandable. So this function right here for the fish is little p of t. This function where we take the cumulative area is capital P. Okay, the next thing we have down here, the word monotone, I don't know how often we use it. I use it very rarely in class, if ever. I don't think we've used it once this semester. Monotone just means one tone. Like if somebody's talking in a monotone voice, it's just one tone, right? No inflection at all. So the word that goes after monotone is either increasing or decreasing. That's what we're looking for. So is capital P monotone increasing or monotone decreasing? Increasing. And do we believe that that's true, even if it's not the fish example? Because every PDF, like the fish, is always above the x-axis. It's a probability function. So it'll never decrease when you start sweeping area. So the capital P is monotone increasing. Next one talks about a limit of capital P as t approaches infinity. What happened to that big blue curve as we went to the right forever? It went to 1. And it actually did get there. It got there at 8, but it could never get there, but it might only approach 1. You might think about what kind of a PDF picture might look like so that it would never quite get to 1, but would approach it. And then going the other direction on the big blue curve, as t approaches minus infinity, we approach 0. Yeah, so this guy right here had to do with tons of fish caught per day. And so it doesn't make any sense to have anything negative for the number of tons of fish caught. But I'll draw a curve that is fairly famous. Just have to try again. You've seen some curve looking like that, the bell-shaped curve? The standard normal distribution. A lot of things in the real world end up looking like this, where most folks are clustered around the average, the mean, and then there are some extremes as you go to the far right and far left, but very few people are out there, which is why the curve is close to the x-axis. So, so the minus infinity says you got to find everybody someplace. So start at the most extreme thing you can find, and then sweep, and you'll pick up everybody. So minus infinity to infinity. The whole area under here forever must be how much? Must be 1. But as you sweep the area, you'll never actually get to 1 because there's still this potential real extreme case way out there. Does that help? Okay, so that is that, I think. All right, and that was that. Okay, so how about 11? How would you find the median of a list of numbers? What does median mean? It is average. Unfortunately, the word average could mean several different things. The middle number when you put them in order, right? So these numbers aren't in order, so you'd line them up in order, kind of like on the money project, 1, 2, 3, 4, 8, with the Lorenz curve and the Gini index, where you'd line people up according to their wealth. The most impoverished person would be the first person in the list, and then the next person would have just a tiny bit more money until you get to Warren Buffett and Bill Gates out here at the far extreme, right? So you line them up in order, and the median in this case is 3, one that's in the middle. So here's the question. Look at the fish. Now, in theory, this represents all possible fishing trips. And some days you might get exactly 2 pounds or 2 tons. Some days you might get 2.01 tons, right? It's possible, and that's accounted for in this picture. So if I wanted to list all the different possible number of tons you might get, like 2 tons or 2.01 tons. How many numbers are in that list? Infinitely many, right? You might get exactly pi tons of fish. That's a possibility. So what's the question? The question is, how do you find the median of the infinitely many numbers that are between 2 and 8 according to how they're distributed here, right? I mean, 6 is the most common number, so it has to have like it has to have more weight than any other number, but how do you do it when there's infinitely many? So on the next page, we're going to find the median number of tons of fish caught per day from this example. So again, we said median was the middle number, which means half the numbers are less than it and half the numbers are more than it. So can you think about where we might be looking in this picture to find the median number of tons of fish? David? 5 is your answer? Okay, so David's guess is 5 tons of fish is the median, perhaps? Maybe 5.5, Tassiday? What do we think of what Tassiday is saying? If you go all the way, you get 100% of the different possible number of tons of fish. We want to find the middle number. That is to say, the place where half the time you get more than it and half the time you get less than it. And so we've got this cumulative area function. We want to find the spot where the area adds up to a half. So we're going to start here because that's where the fish start. And we're going to sweep to the right until we figure we've got half of the area, which is 0.5. So David said maybe it's at 5. Cole said maybe 5.5. So we're feeling like someplace in there. I don't know exactly where. I'm going to put in green here the rest of it. Purple and green are supposed to match if I found the median, right? Half below, half above. So that's exactly what we'll do. Okay, so in order to do this, we need to know what the function is. So it's a piecewise function. I've written it here. You can confirm later on that these equations match those two lines, but for right now, we'll just use them. Do you believe that the half the area point happens before 6? Like if we get to 6, we've gone too far, just looking at the picture, right? Okay, so then I feel like we only need to use the top rule. We're not going to ever get to the bottom rule. Okay, so what we want is so let's say that the median, I think that your book uses capital T. So we'll use that letter. T is going to be the, I think they use T, maybe, I don't know. You want to use M? All right, the people have spoken. M. M is the median. Okay. All right, so then what we are looking for is that the integral from -infinity up to m of this little p of x function is supposed to equal what number? 1/2, 0.5. We want half the area, and the area is always 1 when we have these functions. Okay, so we'll come over here. It's silly to start this function at -infinity. Where do you actually begin picking up area? At 2, so we'll start it at 2. We'll go up to some unknown m to be determined. The only function of those two that matters here is the first one. So 0.04x dx. And I want that to equal 0.5. If you couldn't tell, great question. So if you couldn't, we need to know which one, or is it both? So what you would do if you didn't have a picture or if it was too close to tell is you would actually find the true area in here, right? And you can do that by doing an antiderivative, or yeah, by just doing a trapezoid or doing antiderivative from 2 to 6. You can just go 2 to 6. And if the answer you get is bigger than a half, what does that mean? Then we didn't have to get past there. But if we haven't gotten to a half, all right, then we better include that whole trapezoid plus and then some more. Okay, so we do a little bit of work here. So what does this become? 0.04 x to the second divided by 2, evaluated between 2 and m. And it's supposed to equal a half. The 0.04 was part of the function. I just gave it to you from up here. Yeah, just use that function, the top one. Okay, with your neighbors, can you do this calculation and find m? All right, any questions on getting to the square root of 29 on this one? Is it okay? Okay, and David had suggested 5 tons and Cole suggested 5.5. Somewhere in between those two guesses was the right answer, about 5.39. All right, let's look at okay, so then 13 captures the definition that TAS today figured out for us. The median is the value of t. We used m so that the integral from minus infinity to t of the PDF function is exactly 0.5. Good? All right, and I think that's kind of cool. We just found the middle number out of infinitely many numbers, and they were weighted differently, right? The chances of getting exactly 2 tons is not the same as the chance of getting 2.1 or 3 or 6. But we found the median, 5.39. This is only going to work for an infinite number of numbers, because as soon as you sweep a tiny bit, you've got infinitely many things in there. Yeah. Okay, that's the word median. How about the word mean? How would you find the mean of those 5 numbers? Average means a lot of different things. Add together and divide by 5. So oftentimes, in fact, almost every time when somebody says find the average of the numbers, they really are talking about the mean, right? But we've seen now the median, which is a different way to think of average. So you'd add them up and you divide by the number of numbers. So 1 plus 4 plus 8 plus 3 plus 2, divide by 5 numbers. What is this? 10, 18, what is it? 3.6? Okay, so 3.6 is the mean of those numbers. What question do you think we're about to ask? How do you find the mean of infinitely many numbers? How do you find the mean number of fish caught? We're going to find the mean number of, yeah, that's what we're going to do. There's an explanation here. We're not going to go through it. You're not going to be surprised that it involves slicing into like a little teeny tiny rectangle. This is related to the age example. Remember we looked at the age of the US citizenry. So we've got t is some generic age like 42, and then t plus delta t, we're going to capture all the people that are like 42 years old and 112 days. And if that's not precise enough, then 112 days and 3 hours. And just really whittle it down so that you can say that the people that are in this little rectangle are pretty much the same age. Yeah? If you group together all the people here in the US that are 42 days old and 42 years old and 191 days, then you found people that are pretty much the same age. And if that's not small enough, you'll narrow it down even more. So you have people that are in one room that were all born within the same hour of each other. And then if you wiggle just a little bit, it doesn't change the age very much, right? So, so you can read through the explanation in the book for this, but we're just going to jump to the conclusion right here. The mean is the integral from minus infinity to infinity. You better count everybody, far left and far right, of x times the PDF, the little p of x. X times p of x. Okay, so let's just use that formula. There's work involved in getting to that formula, so I don't mean to gloss over it, but we're just out of time, so we're just going to use the formula. So it says find the mean number of tons of fish caught per day. So remember the mean, we'll just write that formula from before. Minus infinity to infinity, x times p of x dx. For the mean, turns out you just always multiply that PDF thing by x every time. Okay. So the fish function was actually 2 different functions, right? It was piecewise. So we're going to end up with 2 different integrals added up. The first integral is going to go from where to where? Negative infinity to 6, and we're going to be even greedier than that because that function does nothing until 2. So all of the stuff that isn't 0 happens between 2 and 6 for the one function, and for the other function, 6 up to 8. And then inside of this mean calculation, you always do x times, and it is x times the PDF function. So I gave it to you on the previous page. What was the top function? 0.04x, and that's the dx, plus, and then what was the bottom function? Plus 0.6. Thank you.
Why wouldn't you just take the integral of the whole thing and divide it by 8 minus 2?
So let's do that calculation. So Garrett's idea is take the integral of the whole thing and then divide by the 6 difference, right? It went from 2 to 8. So let's do that calculation and let's see what we get. Right, because the total area is exactly 1, right? So the area is going to be 1, so 1/6. Do you want to say that's the mean number of tons of fish caught?
That would be the.
Okay, so there's a mean, so like 16% of the time is like the mean probability, but somehow you gotta get the 2 and the 8 and all the numbers in between in there. Okay, so while we're puzzling over this, can we just get a couple of calculators going? We'll do these 2 numbers separate, so just pick one and do the calculation. What do we get here? 2.5. Okay. So the mean number of tons of fish caught per day is 5.25, which is quite close to what other number? The median is 5.29. So half of the days you get more than 5.29, and half you get less than 5.29. The mean of all those days is 5.25. There is one other M word that we use to measure average. It's what? It's the mode. What does mode? It means most often. So which number of tons of fish was the most often? 6. That was the easiest number to calculate. So 3 different measures of average. Okay, I think we're all done there. The homework assignment for Friday is down below. Project is also due Friday. Work with each other on that. And the quiz. See you on Friday.